In this video, I would like to go over the derivatives of sine and cosine. So far in our class, we've only explored the derivatives of these polynomial type functions, things that are written as x to a power, but we need to move into more complicated functions, some of our transcendentals and other things. So we're going to focus on the derivative of sine and cosine today. And to discover the derivatives of sine and cosine, I am going to go over the limit definition again. We're going to take these functions and find the derivative through the limit definition of the derivative. And to do that, some of the simplifying is going to require some identities. So before we go into finding the derivatives, let's recall two trigonometric identities from pre-calculus. One was the cosine of a plus b, and then the other sine of a plus b. You may remember these as the sum and difference identities. Of course, I only have the sum ones written here. But in case you don't remember, you can look it up, or you can use that awesome flip book you have of identities. But the cosine of a plus b can be written as the cosine of a times the cosine of b minus sine a sine b. You may remember that from accelerated pre-calc on those days during that unit where you were verifying trig identities. You probably use these frequently. Then the sum identity for sine is to do sine a times the cosine of b plus sine b cosine a. Okay, so now let's find the derivative of sine using the limit definition of the derivative, and that may recall us using those identities, so keep them in mind. So I'm going to find the limit as h goes to 0, and I'm going to calculate f of x plus h. So that's going to require me to put x plus h everywhere I see an x in my function, so that's sine of x plus h, minus f of x, which is sine x, all over h. And as you can see here, if we're evaluating the limit as h goes to 0, we have a 0 in the denominator, so we cannot use direct substitution here, and we need to do some rewriting. So the only way I can rewrite sine of x plus h is to use this identity here. Remember, you can't distribute the sign. That's completely illegal. We're not going to do that. So let's expand it with our identity. Sine of x plus h will become sine x times the cosine of h plus sine h times the cosine of x, and then I'm going to bring down the minus sine x on the end. So keep in mind that that sine x is coming right here, is coming from this. I'm just bringing that down. And then everything else is the expansion of the rewrite of sine of x plus h. Okay, oops, it's all over h. Still have 0 in the denominator, so we got to keep doing some rewriting. We have to be careful with the x's and the h, and that we combine things that don't combine things that shouldn't be. What I do notice, though, however, is that this term has a sine x in it, and so does this term. So I think I'm going to just pull out the GCF of just those two terms. That's completely legal as long as I keep the other terms still there. So I'm going to factor out a sine x. That'll leave me with cosine h in the first term that has the box around it, and then in the second term that has the box around it, if I take a sine x out, I'll only have a 1 left. Then this term here in the middle, I'm going to bring down. And of course, it's all over h. So it appears right now that we haven't done a whole lot. It's still a bit confusing, nothing simplifying. But what I suggest is, since you have a monomial denominator, maybe I can erase here in a minute, then you could split this. That was one strategy we used before when doing the derivative. So I could take sine x times the cosine of h minus 1 and put that over h. And then I'll take the second term, which is the sine of h, and the cosine of x, and put it over h. Now, we need to think back to those special trig limits Remember those special trig limits that we learned in Unit 1? Well, look here. Sine h over h, and the limit is as h goes to 0. Then we have cosine h minus 1 over h, and the limit is as h goes to 0. So we need to recall those special trig limits. If we think back to Unit 1, hopefully we will remember in the second term here that this sine h over h, the limit of this goes to 1 as h goes to 0. So we can evaluate that limit as 1, and then using our limit properties, we can multiply that by cosine x. Over here, however, in this first term, the special trig limit wasn't cosine h minus 1. It was 1 minus cosine h. So really, to make this work, we need to factor out a negative 1. If I factor out a negative 1, that allows those two terms inside the parentheses to flip-flop because they'll become opposite signs. And now we have that special trig limit right here, and as h goes to 0, this limit goes to 0. So in the first term, if that limit's going to 0, this whole first term goes to 0, and then I'm going to add to that the limit of the second term. Sine h over h goes to 1, and I'm left with that being multiplied by cosine x. So what we have just discovered is that the derivative of sine x is cosine x. Now, I'm not going to go through this process anymore in the future. I was just using it to prove to you that the derivative of sine is indeed cosine. This is not the power rule. You don't have any powers that you're multiplying in front and subtracting. You're simply going to memorize that if our function is sine x, its derivative is cosine x. Now let's do the same thing with cosine x so that we can discover its derivative. And I will tell you it's not sine x. Okay, so we're going to do cosine of x plus h minus our function cosine x all over h. That's just applying the limit definition of the derivative. And then we want to take that first term of cosine x plus h and we want to expand it using the identity. So it becomes cosine x, cosine h, minus sine x, sine h, and then I'm going to bring down the minus cosine x all over h. Let's do a process similar to what we did before. These two terms have a GCF of cosine x, so let's factor that out. If I factor out a cosine x, I'm going to have cosine h minus 1. Looks familiar. And then I'll bring down the minus sine x sine h. And it's all over h, but we know what's happening here if we're thinking back to our last example. So if it's okay with you, instead of putting it all over h, I'm going to put each individual term over h. Remember, when you're adding, subtracting fractions, you add and subtract those numerators, but you keep the denominators the same. So by splitting it this way, we have not changed anything. Okay, so now we need to look and say, oh, special trig limit showing up here. Except this one does need to be rewritten. It should be 1 minus cosine h. So let's take a minute and do that. The limit, as h goes to 0, I'm going to factor out a negative. And I'll have 1 minus cosine h, if I do that, over h, minus sine x sine h over h. Okay, so here's our special trig limit. Special trig limit. As h goes to 0, this term, this will go to 0, this will go to 1. So if I clean up then, all of this first term has gone to 0, this has gone to 1. The only thing left is minus sine x. So actually, the derivative of cosine x is negative sine x. Okay, so there's no need to go through this process again. We should just from now on commit this to our memory and know that the derivative of sine x is cosine x, and we're going to memorize that. And the derivative of cosine x is negative sine x. Okay, let's work just a couple of examples. I'm not going to work too many with you because really we can work more of these examples after we learn more derivative rules like the product rule and the quotient rule, which is coming up next. Let's work this one here. I've asked you to find the equation of the tangent line. Guys, that's the same process as before. You're going to need a slope and a point. Okay, so why don't we go ahead and plug theta, which is equal to pi, into our function and find our ordered pair that we'll be using, or the ordered pair where the tangent line intersects the graph. So I'm going to plug in pi and evaluate. So 2 plus 3, cosine pi is -1. Know that from the unit circle, so this is 2 minus 3, or -1. So the ordered pair I'm working with here is pi -1. Now to write the equation of the tangent line, I need the slope, and in order to find the slope, I need the derivative. So I'm going to find g prime of theta. Work this like normal. What's the derivative of 2? Well, that becomes a 0. This 3 that's in front of the cosine is going to stay there, and then it gets multiplied by the derivative of cosine. And we learned just a second ago that the derivative of cosine is negative sine. Now, be careful. I put that in parentheses if you're going to write it the way I did because we don't want it to look like we're subtracting sine theta. It's being multiplied by negative sine theta. So our final answer here is -3 sine theta. Notice I didn't use any kind of power rule with cosine. I just know that the derivative of cosine is negative sine, and that's how it transforms. The 3 is a coefficient. It just stays in front and gets multiplied just like it did in the power rule. So now I have to evaluate my derivative at pi so that I can finish writing, or so that I can write my tangent line equation. Sine of pi is 0, so my derivative is 0. Plugging into point slope, I'm going to get y minus, my y1 is -1, so that's +1. Slope is 0, x minus pi. Then, of course, since this whole right-hand side of our tangent line goes to 0, I would simplify this to be y equals -1. All right, so that's finding the derivative with a trig function and writing the tangent line of that. Okay, in this next example, since my video is getting kind of long, I'm just going to find the derivative, and I'll leave you to write the equation of the tangent line. So we need to find f prime of theta. This 4 stays. Then we multiply that 4 by the derivative of sine theta, which is cosine theta. And then I'm going to subtract, and then I'm going to take the derivative of theta. Well, remember here in this problem, theta is like x, and the derivative of x is 1. So the derivative of theta is 1. So that's the derivative for that function, and then I'll leave you to practice writing the equation of the tangent line for this example.